Yeah, hello and welcome to the IFT research call. Today, Hanno is presenting on Waku reliability. Thank you very much. And yeah, the stage is yours.
Cool. Thanks, Daniel. Yes, so I will be presenting a little bit about reliability of a Waku, how the Waku team thinks about reliability. I do want to apologize that this might be a little bit shorter than some of the calls that we've had in the past, simply because we've adapted a small part of a longer workshop that we did at the WPP side event at DevCon. But as per usual, I do start with a definition of Waku, and I'm sure many of you have heard many definitions by now, but I do like to repeat some of the jargon that I think will be most important for some of the points I make later. So Waku is a suite of protocols. It's not just one protocol, but a set of them aimed at establishing some kind of decentralized message routing infrastructure, which will allow communication between two or more points. In other words, if you want to send a signal from point A to point B, or from point A to multiple points, you can use Waku and the Waku protocols for that communication without relying on any centralized services. Right? And some features of Waku that will be important later on is to say that it is based on the peer-to-peer. So we built on the peer-to-peer protocol stack. We focus on privacy preservation. We are DOS protected based on RLN, which I think you'll be relieved here I won't be talking about today. And we focus on generalized communication. That's just to say Waku is not an application. It's also not aimed only at one type of application, but any communication component of any application could, in theory, be decentralized over Waku, right? So if you want to take a look at a kind of diagram like this, maybe the purpose of Waku is to establish some peer-to-peer topology, as you see here. These are based off Waku routing nodes or Waku relay nodes, responsible for routing messages in a kind of like broadcast fashion in a topology such as this. And then maybe you have some kind of communication application represented by these speech bubbles. So here we have 3 instances of an application, and they want to use some nodes in close proximity as entry and exit nodes into the Waku network in order to communicate as an application between these 3 instances, right? So maybe if we look at the green speech bubble here, it wants to send a message to the other 2. So it can use Waku node as entry point, and then Waku is responsible for making sure that this some kind of broadcast routing happening until eventually the other instances of the application can receive this message that was published, right? So note that this is completely privacy preserving. So in other words, all of these Waku nodes in the middle of the topology have no idea what it is that they are routing, where it's coming from, where it's supposed to be going. They don't know how many intended recipients there are. This is completely agnostic on the Waku layer. That means from an application perspective, Waku can just be this abstract idea of a communication medium, right? So these application instances just plug into this communication medium, and all they know is that the messages that they're pushing on the one side kind of like pops out on the other side. And in fact, in a properly designed application, it should be possible to just remove Waku and replace it with any other communication medium, and the application should function in exactly the same way, right? So knowing all of this, what is the problem of reliability within Waku? Right? So I think it's quite simple from the application's perspective, and this is the most important perspective. What the application wants to know is, do the messages that I kind of publish over this communication medium, do they actually reach my intended recipients? And I would add to this the question of latency. So do these messages arrive in a timeless fashion? That's also an important consideration for us under reliability. Then maybe a bit more abstract is the idea of the knowledge of message state. So it's not just about whether these messages do reach their intended recipients, but also how much can I know as an application participant about this? Do I know that these messages have received, kind of been received by the recipients? Do I know that they are messages that I'm not seeing, that I'm supposed to be seeing? All of this is part of the reliability problem. And let's imagine that we can kind of look under the hood, so we understand that this is a Waku network doing the routing, so we're not just the application thinking of this as an abstract communication medium, but we can see how things can go wrong here, right? So let's imagine this Waku node here has run out of memory. It's immediate. Waku nodes around it might not know about it right from the beginning. So something has gone wrong on the Waku routing infrastructure. And now, of course, if this application instance wants to send a message, it won't go really far, right? And the other application instances would now sit with the problem of reliability. That is, how can they know that they've missed this message? Is there anything that we could have done better? Given kind of like just even visually looking at this, what things could have been improved here to achieve reliability, right? So I would say within Waku, we think of the problem of reliability on at least 3 different layers. These correspond to the layers of the Waku protocol stack, from the lowest layer to the highest layer in the stack. The lowest layer, we have this transport reliability, which is the reliability within the P2P layer and transport itself. I'll expand a bit more on what that means. Then on top of that, we have what we call peer-to-peer reliability. This is within the Waku protocols that we built on top of the peer-to-peer. This is a type of hop-to-hop reliability. So this is within this topology of Waku nodes communicating, some kind of reliability to ensure that messages are indeed routed between your direct neighbors or between 2 different hops within the Waku network. But all of this eventually doesn't mean that much to an application without end-to-end reliability. This is at the highest layer, the application layer. This is the most important, because no matter what we do on transport reliability and peer-to-peer reliability, none of these things would ever guarantee the kind of end-to-end reliability that requires the application-specific knowledge to know intended recipients have received a message that was published. So just to look a little bit more in detail at transport reliability, this is the lowest layer that we consider within Waku. Basically, this would be the reliability of the underlying peer-to-peer protocol stack. Right? So Waku is mostly based on peer-to-peer gossip sub. Our version of gossip sub is called Waku Relay. So by approximation, if we say transport reliability, we mean how well does Waku Relay or how well does gossip sub function, right? And there are many things we can do, right? So we can think about how we configure the transport protocols for the gossip sub connections. This can be TCP. One day maybe it can be quick. This can be WebSockets. And this also has an effect on the reliability of just the functionality of gossip sub itself. We think here of things like redundancy parameters. Gossip sub could, for example, have redundant connectivity. It has tunable amplification factors. Amplification factor is just how many copies of a message do you send. Of course, the more copies you send, in theory, the better reliability you might get in terms of propagation in the network. But that can, of course, also affect scalability. This also affects latency, which I mentioned as part of reliability. So these are things which we are concerned about in terms of gossip sub. Peer diversity is a very important subfield of what we do. This mostly relates to our discovery methods. So if you have a proper discovery method, that is, how do you find other Waku nodes in the network? If you have rich connectivity, that is, peers from all over, in a sense, with good diversity, you can improve your resistance to things like local outages. It means that you won't be affected by many adversarial kind of conditions or Eclipse attacks as much, because you have a wider exposure as a node to the network. And then I think we can kind of skip over details about things like disconnection detection. It's just making sure that your gossip sub connections actually you can detect when they go offline. can use the peer-to-peer pings for keep alive. And these are all mechanisms which we have worked on within Waku. Then, if we go a layer above that, we might be on the Waku layer. So this is just above the peer-to-peer. This is mainly aimed at thinking about the reliability between different Waku nodes. So all reachable Waku nodes can kind of like have hop-to-hop reliability by doing some things within the Waku protocols. Right? One thing that you might do, for example, is just get an acknowledgement that the message that you route as a Waku relay node to a next hop has indeed been received by that hop. This you might do when you use a protocol such as Lightpush. Lightpush is just a lightweight publishing protocol, and indeed it returns an acknowledgement from the next hop node that yes, I have seen this message that you've pushed to me. We think of things like protocol combinations here, such as filter and Lightpush combinations, whereas Lightpush is a lightweight publishing, filter is lightweight receiving of messages. And you can then, do some clever things here. So maybe if you publish a message, you can use multiple filter installations to probe the network at different points, different hops in the network, to see how well the message has propagated into the network, and maybe achieve some reliability there. I also include Waku Store queries here. Waku Store is our historical message storage protocol, so caching of messages that are being routed in the network for a certain number of hours. And this can be used by nodes when they go offline to retrieve messages that they might have missed during their disconnected period. So for that reason, relates to reliability as well. And we do some other things with Waku Store, for example, to check that the message that you published have indeed been published or been seen by the store. We can use it to fill in gaps in your own kind of local history as well. Very much related to that is a brand new protocol, which SP is developing and has developed to a large extent, which is called the Waku Sync protocol. Think of it as it's almost like a CRDT layer, which is established over Waku, conflict-free replicated data type. It's just a fancy way of saying that nodes that are caching messages, specifically Waku Store nodes, can use the Waku Sync protocol to reconcile their messages, so they can synchronize with each other. Maybe they've missed one or two messages due to temporary outages. They can use this protocol to make sure that they fill in those gaps and that everyone agrees on what messages have been routed in the network in the past X amount of hours. So of course, that also relates to reliability. Note that all of this happens on the Waku layer, so remains completely agnostic as to what applications are actually looking for, right? So we don't know anything about the applications and what messages they're sending, because we don't have access to that information within the Waku layer. So that makes these measures quite expensive, right? Because if you operate on the entire routing layer and all messages of all applications being sent around. So we mostly use these protocols for now for very targeted use cases, very often in terms of our service infrastructures, where we need these kind of hop-to-hop guarantees. But because these are very resource intensive, we don't use this as a main form of reliability, because it cannot still not really provide the kind of end-to-end reliability that applications need, which is, as I've mentioned, in some way, the only meaningful reliability from a user's perspective. So this is the application with the full knowledge of what messages should go where, is only interested in this kind of reliability. In other words, app-level reliability is the end-to-end reliability is an app-level reliability that spans the entire network, and even the kind of entry and exit points into the network, more or less agnostic of Waku itself, right? So for that reason, if you want an end-to-end reliability protocol, it needs to be embedded within the encryption layer of whichever application is using this. VAC has developed such a protocol before. It's called the Minimum Viable Data Sync, or MVDS protocol. But it turns out that this is not very scalable, especially when applied to large group communications. I'll try to illustrate a bit later why not. And for that reason, we've been working on the STS protocol, the Scalable Data Synchronization Protocol, which will be the subject of the rest of my talk, right? Okay. So Scalable Data Sync Protocol, or STS, is Waku's solution for app-level end-to-end reliability, right? And specifically with bearing in mind that this is over some kind of broadcast transmit, such as gossip sub or Waku relay. I keep referring it gossip sub to ingratiate myself to the low peer-to-peer team. So imagine that you're part of low peer-to-peer now. So we think of some kind of group communication scenario within an application over Waku. And the model that we use to design this protocol is the model of the consolidation of distributed logs. Okay. Make it a little bit more clear. The first application that we are designing this for is for a group chat application, and specifically for status group chat or for status communities. So if you think of a group chat, each participant in the group chat is maintaining a log locally, which is kind of the log of the conversation. It's the history of the conversation. All messages in order as they were sent within the group chat. And the problem of reliability then becomes to make sure that everyone has the same view of what messages have been sent in the group chat and in what order. And when you want to send a message to the group chat now, you just append it to your local copy of the log. And the STS protocol is responsible for reliably transmitting this append operation to all other participants of the group chat. Okay. So we aim for partial causal ordering and differential consistency. I will define these terms a little bit better, but they might be apparent based on what I've said. But the thing I want to emphasize now is we do design this protocol for large-scale dynamic participant groups first, because we believe this is the hard problem to solve. And if you have a protocol, a reliability protocol that works for large group communications, in theory, it should also work for a more simple case, like a one-on-one chat scenario, because a one-on-one chat is just a special case of a group chat with only 2 participants, right? So that is the mentality or the mindset with which we have approached the STS protocol design. To expand a little bit more on the kind of scalability challenges that STS protocol needs to address, let's think of a hypothetical chat scenario where you just have a very simple one-on-one chat or a very small group of participants who want to communicate with each other. How can you introduce reliability in that chat, right? Because it's such a simple scenario, maybe each participant can just acknowledge every message that they send directly, right? So I sent a message and everyone in the group just tells me, yes, seen it, seen it, seen it, seen it. You might have some direct sync requests for missing messages. So everyone in the group just synchronizes with each other. And the point is that even if you use some broadcast type transport here, so even if these interactions, these acknowledgements are broadcast to a large group of people, the number of these interactions are relatively low because you have a low number of participants, and you don't necessarily need to think about scalability so much. However, if the size of the group will increase, you will have an explosion of kind of direct interactions here, the acknowledgements, the sync request, the retrieval request that arises from each individual participant in the group, and each time is broadcast to everyone in the group. And this increased redundancy and resource usage really risk flooding the network. And I have some pictures to make it a bit clearer. So now this topology that you see is not a Waku network now. This is a representation of a group chat. So we have 5 participants in a group chat, and they are using some broadcast transport to communicate with each other. So every message is broadcast. And so this could be Waku. So let's imagine they are using Waku in the back end, but this is from the application's perspective, right? So one participant in the group, the red node here is planning to send a message to everyone else in the group, and it does so. It uses a broadcast transport, such as Waku, and everyone has now received this message, right? So the red message is everywhere. Okay. If we assume that they are using a naive acknowledgement mechanism to introduce some reliability here, right? So we want to make sure everyone has received this message. Well, what we can do is this node now here might just decide that, okay, it's going to acknowledge the message as it has received it. And indeed, it sends an acknowledgement back to the originator of the message, the publisher. But of course, it's using a broadcast infrastructure. So this acknowledgement would be broadcast to everyone else rather unnecessarily. But then, of course, everyone is running the same heuristic or the same protocol. So all of these nodes will also be sending acknowledgements to everyone else, right? So one message that you've broadcast has resulted in a massive explosion of acknowledgements going everywhere in the network. It's a very naive protocol, but this illustrates roughly the problem of scalability that we need to address with the SDS protocol. Okay, so what do we do? We want a protocol that can be scalable, but still provide at least partial causal ordering and eventual consistency. And these terms just mean that within a reasonable time period, all participants in the group communication should agree on what messages have been sent and in which order they should be represented in their own copies of the communication log. So that's the ordering and the consistency. As far as possible, we want to piggyback on existing messages. So we want to add some information to messages that's already being broadcast in the group, and maybe add some things that allow us to derive ordering and consistency using that. We also want to be a little modest, I think, at least in the beginning of the level of certainty that we need to build into this protocol. Maybe, for example, for a publisher, instead of needing to know that everyone in the group has certainly received a message, maybe it's okay to just infer that your published message has been received by a subset that's large enough for there to be a relative high probability for everyone else to be able to receive the message at some point. And then indeed, we can make it the responsibility of these recipients of messages to determine themselves if there are missing messages. So this is determining gaps in the causal history. Causal history are just messages that have been sent in the past that you haven't seen yet. And yes, so because we are working on a broadcast infrastructure, we have to keep this in mind. We want to limit expensive interactions and kind of focus on the most cheap way of propagating messages. So this is why we prefer an eager push mechanism to propagate new messages quickly. If you publish a message to a group, this is a one-to-many interaction. So there's only one source of the interaction to have to broadcast a message. But if you are too eager to pull messages as a recipient that might have missed some messages, this might be a many-to-one interaction. So there are many originators of these interactions. Each of these interactions would have to be broadcast. So that's why we prefer eager push and lazy pulling in how we approach the SDS protocol. Okay. The features that we have added now to the SDS protocol. So, and these are features that we piggyback onto existing messages as far as possible. We include Lamport timestamps. Think of Lamport timestamps as a logical clock or just a simple sequence number that allows us to achieve causal ordering in the network. Then we include a causal dependency directed acyclic graph or a DAG to detect missing messages. Fancy way of saying that messages are now aware of messages that have preceded them in the past, and they in a sense depend on these messages being processed first before you can process this message. So they have some references to past messages. We also include a Bloom filter as a type of window of past messages from a publisher's perspective to provide a probabilistic way to acknowledge messages as well. And then these three features that the protocol introduces. Can be used to do dependency checks, checking that I've seen all messages that I should have seen before receiving this one. Acknowledgement checks to see that my message has indeed been published, and conflict resolution and delivery. That is to say, if making sure that messages are ordered consistently, even if there are clashes on the lamp or timestamp, which happens quite frequently. Yeah, so previously maybe you just did the message payload. This is what you sent to the group, group message. But now we add a little bit of information here. So there's a message ID. This is just a reference to this message, or a hash that uniquely identifies this message. It's a lamp or timestamp, just a monotonously increasing sequence number in a sense. Partial causal history. These are references or the IDs of the messages that, from the publisher's perspective, precedes this message in the group communication. And then a Bloom filter, which is a bunch of bytes that represent past messages that that you have received as the publisher of this message. Okay. So how do you now send a message with SDS? So messages are published over Waku Relay, as we know, but they are considered unacknowledged by the sender. And we make it the sender of the message responsibility to periodically rebroadcast this message. So this is the eager push mechanism, until it has received sufficient acknowledgement of the message within the group. And the ways to acknowledge a message would be to see if it's included in the causal history, the causal DAG of received messages, whether it's included maybe more probabilistically within the Bloom filters of received messages. And yeah, okay, again, I think an illustration will be easier. So we're back to our group chat using Waku as transport. Red node again wants to send a message. It does so, and everyone has received the message. Now we don't have any of these silly acknowledgements just being generated and published all over the place. Instead, we are waiting for the next message to be sent. So sometime later, 10 seconds later or whatever, the blue node now wants to send a new message to everyone in the group. And what it does is it crafts the blue message. But now instead of just sending a new message, it will include some form of a reference to the red message it just received. And it will forward then this message, broadcast this message to everyone else. Okay, the first thing that can happen is you can see that the original publisher of the red message can now answer the question whether this red message has been acknowledged, because at least it's been acknowledged by the blue node because it includes a reference to this message in its own message. And then if you've been paying attention, you would see that, okay, all of the other nodes in the group chat might also be able to use this information to ask themselves some questions. So they now see a reference to a red message, and maybe they can ask themselves, have I seen this red message? And if not, maybe there are some remedial actions I can take to wait for this red message. So this red message, in a sense, a dependency for the blue message. Okay. So yeah, to go in a bit more detail, then what happens then at the recipient? The recipient receives now a message with this protocol, and the first thing it can do is it can use the included lamp or timestamp, this logical clock, to order the message inside its own local log. And yeah, then this kind of guarantees a consistent view of the order for all participants in the group communication. But it can also look at the included references to prior messages, the causal history included in the received message, to see if it has met all causal dependencies. So just saying, if it has already received these messages that's referenced as prior messages to the one just received. And to kind of buffer this message, perhaps, until it has received these prior messages, right? So if you receive a message with unmet dependencies, that is, there are some prior messages that you're missing, you can buffer it, And at some point, you might even decide to try and fetch these messages from using some either peer-to-peer means, or in Waku's case, we also have a Waku store from which you can try and fetch these unmet dependencies. Just some features of the SSS protocol that didn't neatly fit any of the other slides. If we just piggyback on existing messages in the group communication, the protocol might behave very slowly, right? We might want to have more periodic sync messages, don't contain any other content, but it's only there to maintain state and reach consistency a bit faster. So that we have addressed in the protocol as well. We have periodic outgoing and incoming buffer sweeps, just to keep the acknowledgement status of published messages and the kind of dependencies, unmet dependencies of incoming messages clean, and to do some housekeeping there to try and retrieve messages that you believe you have missed. And in the very worst case scenario, maybe say some messages are retrievably lost, but at least give the application some indication of that. And within Waku, we often have this idea of ephemeral messages. These are messages that only have value for the short period after it has been published, and they don't really need to be broadcast reliably. So we want to make sure that there is also consideration for messages that want to be published without any reliability overhead. Some conclusions about the STS protocol then. So yeah, we work on this idea of the separation of concerns. We have gossip stuff, well, Waku Relay for the broadcast type infrastructure, and then STS for an application level reliability. But as soon as you consider application level of reliability, the fact that you're using a broadcast type transport does raise scalability concerns, especially for large group communications. So Waku leverages STS to achieve in a scalable way the partial causal ordering and eventual consistency that we need. One thing I didn't really talk about at all was that STS tries to offer tunable scalability. That is to say, if in some deployment scenarios of the protocol, you don't need this much efficiency and you prefer to achieve faster consistency, for example, you can tune down some of the efficiency parameters of the protocol itself. People might be interested in the current status of this work. So all of this was sparked by a forum discussion, which is now quite old, but I think there's a lot of valuable historical information and conversations also with the status team for which this was developed initially, and is still being kind of integrated there. So feel free to look at that. But that eventually did spark a raw specification, which has been published on the RFC index repo. Do go read that and do provide feedback. We have some ideas as to how this protocol needs to evolve in future, and any input would be super welcome, especially if you have some experience in this field. We have a working PRC implementation, by the way. So this is, and I mean with that, this is a chat application that uses STS for reliability. You can download that and run a reliable chat protocol between two instances. And I have the link right there. As I mentioned, this was mainly designed to introduce end-to-end reliability within status, specifically for status group chats and communities. For that, we want to not just add things to the current status stack, but in a way neatly provide an API that can be called from within status Go to handle all of the reliability logic. And there is a forum post that proposes some kind of API specification. So thanks to Akil for doing that. And that conversation is ongoing, but will eventually lead to also a separate specification document. However, we have begun implementing this very API library that you can find in the NEM end-to-end reliability repo under Waku.org. and also see the work in progress as we add more and more functionality there. And that's it for my talk. Let me just navigate back to where you are. Any questions? Did I miss any in the chat, maybe? Could people still hear me? That would be sad if no one could hear me.
Yeah.
Good.
I got a question. What does the process look like for verifying this and then implementing it within status such that the user experience within status is reliable?
That's a good question. So the first thing that we want to do here is just work on that aspect that I mentioned, the knowledge of message status, I think, and I think we can do much better there, right? So for status, what we will try to do is retrieve messages in a sort of cheaper way, which is to say we use the Waku store, and we can determine that messages are missing. But now, because we have this idea of a distributed log, each participant should have the information of which messages am I missing and which of my messages are not really being published to the network. And we will tweak various remedial actions to get that better and better. But I think we will have that information available now in a much more, a slightly more certain way than it was before, right? Well, not much more certain way than it was before. You will be able to see in your chat log, I'm still waiting for some messages that precedes this one, and I have a message that's not quite delivered yet. So I don't know if that answers your question, but we have the information now within each client to have that.
Okay, great, thanks.
I have a question. Thank you for the live presentation. We want to use the Waku messaging between the admin communication in the decentralized MLS. Is there any kind of numbers, for example, like simulation, number of nodes and epochs or time to or success probability of receiving the messages, for example, a 1K or in some epochs in time or in seconds? Do you have?
You mean for how well XDS protocol works
Yes.
in those scenarios?
Yeah.
No, I think we're at a very early stage here. I mean, we can make some guesses based on various probabilistic kind of models. But to be honest, I think it's quite complex. It's a complex interaction of how well the Bloom filters work, how we tune certain of these parameters, and we're just not there yet. What we have is a very simple implementation for a chat application, but we didn't try to scale it or anything. So I don't think we have that information yet.
We will put this on a DST roadmap, so as soon as that is mature enough to be tested at scale, that would be nice. And as you said, like mathematically modeling that is definitely possible, but yeah, that takes more effort than just simply measuring gossip. So
yes, unfortunately.
I would also have a question related to MLS, and that is like you mentioned the this tunability of the reliability property, and what if we would just drop the Bloom filter completely for some groups and just add more information to the deck and then get would that be a way to get full reliability and for a specific content topic and for a specific pub subtopic? What I was thinking is if we could have just one pub subtopic with guaranteed reliability, then we could use that one for establishing the MLS keys.
So this is something I have considered, but I think it will be difficult to do. In essence, you would have to always recompute your entire causal DAG, and maybe modify the DAG of past messages in a way to be able to traverse all the way back to history. So what is happening here is that these DAGs are just from each individual node's perspective, and we don't cover full history. So what might happen is that there could be messages that branch off your DAG in a certain direction, but never necessarily appear themselves again in the causal history of any other messages, right? So because these are independently maintained logs, and you're just merging them. I guess my answer is it might be possible, but it is quite difficult to do.
But yeah, I mean, even if like it's definitely like too much work for most use cases, but like for very specific pops up topics, let's say for the MLS key establishment, because if we could pull that off, then we could get rid of the on-chain component, and it's like that might actually be worth it.
Yeah.
And so we could also think about having a set of more stable nodes that can help with the ordering, and then it would not be a federated system. It would still be like just some type of super peer system. I mean, I'm just thinking how to get rid of this, the on-chain component, and still have a subgroup of users within a group being admins. So having one admin for MLS, that's easy to do, and but having a subset of the users in a group being admin, which means like the rights to add and delete users, very difficult. Without, like, I mean, you need the total ordering to be able to pull it off. And yeah, but maybe we can think about this for just some very specific use cases, and also for ACZ to let's put this on our agenda. Just for reference, there has been a talk about MLS. I think it was like the last one or the one before that. It's linked in the schedule, and it's also on YouTube.
Yes, I would indeed. I would like to see this happening. The one thing in the design of this protocol which I didn't like was actually that you have both a causal history and a Bloom filter, but it was sort of difficult to get past that.
I think it's nice. Like, it's nice for the for the chat application. I think this is actually, it also fits well with Waku's tunable, like configurable protocols, and like along various dimensions, and like for some specific pops up topics where you want to have guaranteed delivery. The question is if we can make this happen that is actually similar to a TLS level guarantee of like getting a message delivered. In the normal context, I actually think the Bloom filters are very nice, because then you have like it's like, for some, like if you see it in a DAG, you're certain. If you see it in a Bloom filter, you like have high probability. And you could even go as far as like for specific messages saying, okay, this message, I want to have the higher level of certainty, and you wait until you find it in a DAG and you continue eagerly pushing them.
So that's actually the idea, is if you need that high level of certainty, you just continue publishing the message until it is actually part of someone else's DAG. That is the responsible the way in which you can get that certainty. Also, the Bloom filter, by the way, is very useful for us for a certain NAC, right? So for a negative acknowledgement, and that addresses the problem that is the main problem here. Is most often a publisher actually just failed to really publish the message. Most often, when a message has received the Waku network, it actually reaches its destination. But we see from status perspective specifically, when a message goes missing, it's most often because it actually was never published, but there was no way to know that it's never been published.
How does this happen? I mean, like how can this happen? So like,
Well, because there's usually undetected short disconnection periods.
Oh,
and-
yeah.
So that is the case that we most often see. So the application believes it has communicated with Waku. Waku believes it has published, but actually it's it has been disconnected, but it's not been disconnected for long enough to actually have detected that.
but shouldn't your local node be able to detect this?
Yes, but I think with TCP, there's a time period where you can't detect it, so there's some timeout, and it's usually in that you just, I don't know, drove through a tunnel or something. Yeah, so we saw this a lot. Yeah, and of course we can try and improve that, but that wouldn't address the full problem. But indeed, in this case, it's the sending of the message is the one is where it often fails.
But that would be interesting to look into if this, if this can be done. I mean, just note for myself, like look into if this can be done.
Yeah.
On the client side.
Yeah.
Just for this specific case.
Yeah.
To get even faster feedback.
Yeah.
Yeah. Thanks a lot. That's great. Yeah.
Awesome.
Yeah.
Cool.
Do we have any other questions? Yeah, but actually, this is actually really nice. It really seems that there's hope for getting MLS. Is like I'm just thinking for the communities, for status communities, or for specific scenarios where we might not need this on-chain component, because it's kind of it just adds complexity. And if we could use this protocol, use STS for it, that would be really nice.
Yeah, I'll be very happy to see that.
Yeah,
I think it is possible.
Yeah, let's definitely put some of the research effort for ACZ into this for next quarter, like commitments for Q1 2025. Yeah, but then if there are no other questions, thank you so much, Hanno, for the very interesting talk, and also for taking this on quite short notice, after DEF CON. Yeah.
My pleasure.
Thank you very much. And again, saying this again, so this recording will be on YouTube. It will be linked in the schedule, and there will also be a VAC forum post where we can continue the discussion. So Philip will put a transcript of the discussion into the forum, and yeah, we can continue the discussion there. Thank you very much, and see you in the next call, which will be on the 18th of December on Gossip sub improvements. Thank you.
Cheers all. Bye.